Hi, this is a quick, maybe not so quick video on horizontal projected motion, but using all variables. Something that we didn't practice as much as I had hoped in class, so I'm going to make a video so that you can hopefully learn a little bit from that. All right, so let's maybe visualize it. So I just went online to find a simulation of something that is horizontal projectile motion. So I've got a PhET simulation here. So let me just erase it here. And we're just going to fire an object, right? If I just erase the trajectory here, I'm not going at an angle, I'm just firing this off horizontally. I'll give it some initial speed, say 24 here, and then I'll just fire it here, okay? All right, and it's not firing for some reason, there it is. There you go. Let's say we change that speed to a slower speed, and then we fire it, there you go, right? So we want to develop an expression for the time that it takes to get down to here. Notice it's if you look at it here, that time is 1.4 seconds over here, and that time over here is also 1.4 seconds. Notice that even if I change that initial speed and I fire it, the time that's in the air is only depends on essentially the height. It's exactly the same time for all three of these trajectories to go down to the ground. So I'd like to develop an expression for that. All right, so let's set it up by drawing a picture to kind of visualize what's going on. So I'm going to have, let's say I have a table here, all right? And then I have the ball being fired off with initial velocity v sub 0. I'm going to show the parabolic trajectory, all right? And then I'm going to label some information that I know. I am told that the height of the ball from the ground is h. Okay. So we are trying to solve for an expression of the time in the air, right, in terms of h and g. Okay, so we want to know how long is this ball in the air for, right? So when I solve these kind of problems, I like to write down organize all my known and unknown variables. So I'm going to, just to make it a little bit easier for us to understand, I'm going to break it up into sort of two columns, a horizontal column and a vertical column of information that I know and I don't know, right? So we'll start off by, for example, saying, what about the acceleration? Horizontally, what about the acceleration vertically? In the horizontal direction, if we assume no air resistance, the acceleration is 0. But vertically, it is accelerating. There is gravity acting downwards, right? So we do have a vertical acceleration, and that is negative g. It's like negative 9.8 meters per second squared, but we're not going to use the number. We're just going to use g instead, right? And we have a negative because it's going downwards. Okay, the next thing I'll do is maybe talk about the initial horizontal position and the initial vertical position. So what we need to probably establish here is a coordinate system, right? So we're going to assume that the y points straight up and the x points to the right, and we'll put our origin right here. So we have a positive y-axis there and a positive x-axis over there. Okay, so therefore, all right, our x initial is 0 and our y initial is actually h because it's starting at a height h here. Okay, the next thing we have is the initial horizontal speed and the initial vertical speed, right, or velocity. So it is being fired horizontally, so it doesn't have any initial vertical velocity. There's no component in the y direction. So the initial vertical velocity is 0, and that's mentioned also, a reminder right here, right? The horizontal velocity, because it's being fired at v sub 0, well, that is actually the horizontal velocity too. So v sub 0 is, or v naught, is the same as v naught x. Okay, next thing. When the ball is just about to hit the ground here, right? We want to know what its x position is and what its y position is. So it's just about to hit the ground, so we can assume that its y position is approximately 0. But its horizontal position, this distance here, we don't know what that is. So I'm just going to put x equals question mark, right? We'll put a question mark here. Okay. Whoops, I keep on pressing the button here. Next, we don't know what the time in the air is. In fact, that's what we're solving in part A. Okay, so once we've established all the sort of knowns and unknowns, then the next thing is to sort of tackle what equation do I use? And it really comes down to, do I use the equations along the x-axis or do I use the equations along the y-axis? So maybe you start off with this equation. We start off with the x equation. X equals x naught plus v naught x times t. plus 1/2 axt squared. And then you know that the acceleration horizontally is 0. The initial position is 0. And so we get basically x equals v naught, because that's what we're replacing it here, multiplied by t. But the problem is that we want an expression for t that's not in terms of x and v naught, but we want it in terms of h and g and v naught, right? So we need to be using these variables, or at least one or two of them at least, right? So that's not going to work. So we'll come back to that equation. That's not the approach. We're going to be actually using the vertical motion, right? So we're going to use y equals y naught plus v naught yt plus 1/2 ayt squared. Okay, so now let's plug in here. Our y final, just before it hits the ground, is 0. Our y initial is h. Our initial vertical velocity is actually 0, so this whole term disappears to 0, right? So we'll put plus 0 if you'd like, plus 1/2 times negative g for our acceleration times t squared. So this is really negative 1/2 gt squared, so you have 0 equals negative 1/2 gt squared. But let's bring that on the other side, so we get 1/2 gt squared equals h, and we're solving for t. So I'm just going to scroll down a little bit here. So to solve for t, or let's say we solve for t squared, we're going to multiply both sides by 2 over g. So it'll give you 2h over g, right? And then now we need to take the square root of both sides, so we get t equals the square root of 2h divided by g. And that's it. And you may notice that the time in the air only depends on what? The height that you release at and the acceleration due to gravity. So if you go back to our animation earlier, and I was showing you that the time here was 1.4 seconds. Over here it's also about 1.4 seconds, and over here it's 1.4 seconds, and they're all, or 1.43 to be exact, they're all the same time because they're all being released from the same height, right? And there is no like vertical motion. Now if I had fired this guy up at an angle and just a tad, and I fired him right here, let's see if I can do that, come on, you'll see that this time in the air is not. Now if I time that, that's longer, it's 2.1 seconds, because now there is a vertical velocity. And so our expression for the time in the air is going to be different. But if you fire them all horizontally, then all three of these trajectories have the same time in the air. Okay, so what about the next part? The next part asks for the final speed at which it hits, right? So maybe I will copy and paste this diagram over here if we can. All right, let's copy and paste. All right, can I move that over there? Let's go Command V here. There we go. And we are solving for the final speed, right? So we want to know the speed that this hits at. So let me draw the velocity vectors. Imagine the ball's like right here and it's flying through the air, right? Let's maybe draw some velocity vectors on here. So I'll maybe make it like pink here. So the horizontal velocity is to the right, to the right, to the right, right? But the vertical velocity, all right, is going to be going, well, there's none here, but it goes down and then it gets bigger. And what we're asked to find here is actually the resultant velocity. We want to find out what this v is right here. So we're looking for what v is, an expression for that in terms of v naught, h, and g. Okay, so I hope that you can sort of see this as a right triangle, that you can make a little right triangle in here and think, okay, you've got horizontal speed this way, which is v sub x. You've got the vertical velocity going here, which is vy. And we're going to move this guy here, and we're going to make it come over on this side, right? Move that guy over there as well. And then really what we're doing is we're finding this resultant velocity there. We're trying to find out what v is. All right, in order for us to find that, we need to find an expression for vx, an expression for vy, and then we're going to find v by using good old Pythagorean theorem. So v squared equals vx squared plus vy squared, so v equals the square root of that. So this is the idea we're kind of going for, right? So in order to solve this, we'll start with that. V equals the square root of Vx squared, the horizontal speed squared, plus the vertical velocity squared. And we need to put some expressions in here, right? So the horizontal velocity, if you recall, is the initial horizontal velocity plus the acceleration multiplied by the time. But of course, it's not accelerating horizontally. So therefore, what we find is the horizontal speed later, like here, is the same as the initial horizontal velocity. These are all equal. You notice I drew each arrow the same. So this is really just equal to v naught. What about the vertical velocity? Well, the vertical velocity, we're going to use the same equation. V naught y plus ay times t, right? And the initial vertical velocity is 0. And now we're going to substitute in 0 minus or plus negative g times t. So Vy equals negative gt. So we can plug that in here, and we get V equals V naught squared. We're replacing the x quantity here with V naught. And then, of course, we're going to replace the Vy with this expression. All right, so we get plus negative g times t quantity squared. But, I'm happy with this mostly, but my problem is the t here. And I don't want an expression with t in there. So I have to get rid of that. So maybe I want to develop the Vy velocity expression a bit more. So is there something that we can replace the time with so that we get rid of the t, right? So let's do another replacement. What does t equal to? Remember what we derived earlier. T equals square root, right? Right over here, right? We got this expression here. Why don't we plug that into here, right? So we're going to put in, replace t with square root of 2h over g. So our new velocity equation in the y direction will be negative g, the root of 2h over g. Now I could simplify this, but I'll do that later on. So now let's replace this whole expression in for there. So that's going to maybe, I might not have enough space here, but I'll try to fit it in here. It's going to be negative g square root of 2h over g quantity squared. Okay, so if you can probably just leave that if that was like an AP exam. They don't penalize for simplifying, not simplifying, but I'd like to have things nice and clean, so I'm going to simplify this. So I'm going to read v naught squared plus, okay, what's going to happen here? We have, well, the negative squared just goes away. There's no more negative. It's just g squared. Then multiplied by, when you square the square root, you're going to get rid of it. So it's going to be 2h over g. So this then gives you, if you simplify this, v naught squared plus, well, one of these g's cancels out, plus 2gh. And voila, that's the expression for the horizontal, or the resultant velocity when it hits the ground v. Okay? And of course, that's only, by the way, you could use that expression if it was only being fired horizontally. By the way, I should just remind you that these expressions that I'm deriving are not things that you should just like memorize, right, and just plop them onto the into your solutions. You really need to know how I derive them and how to derive them from first principles. Because remember, if the equation is not on your formula sheet and we're deriving it in class or in a video, then you need to know how we got there. Okay, you can't just like write it down just because you memorized it. Okay, moving on. Now, part C, we are doing the horizontal range. So we're going to take this guy. Did I paste that? Can I paste that picture again? Oh, yeah, sure. Why not? All right, so there we go. We're doing this now, except we're asking for the horizontal range. And the symbol we use for it is basically a, cancel that, is a R, right? So X is R. R stands for range, like you're at a golf range, right? How far does it go horizontally? Okay, so now, once again, we need to find an expression for R, but in terms of H, G, and V naught. So we need to probably use something with an X in it. And you may recall earlier when I started part A, I was using this equation, and I got nowhere because I had a T in here. So that's kind of what we're going to use in that equation. We're going to use this horizontal motion equation in our last part, which is for part C. Oops. Okay, let me scroll down here. All right, and here we go. So we'll start off this solution writing our horizontal motion as a function of time. X equals x naught plus v naught xt plus 1/2 axt squared. We're going to get rid of the last term because we know that the acceleration horizontally is 0. We're also going to get rid of x naught because we're going to assume that it started at the origin. All right, horizontally speaking. And now we are just going to be having just v naught x times t, where we know that v naught x is just the initial horizontal speed, right? And we also derived an expression for the time in the air, and that was done way back in part A. Remember, square root 2h over g. Good to know that derivation, right? So that's equal to 2h over g. And we're going to plug that into here, and we get x equals v naught multiplied by square root 2h over g. And that's it for that. Okay? So you can see that that the horizontal distance that it goes at, let's see if I can put that up here. So how far it goes, like let's say if I erase these trajectories and I just fire it horizontally, and let's say I fire it at a speed of 20, right? And voila, that's where it goes. But then if I fire it at a speed of, say, 10, right, and I see where it goes, you'll see that the range here, this is about 14.28 meters, and then over here, guess what it's going to be? 28.56. It's double, right? That's because the horizontal range is proportional to the horizontal speed. So the faster you fire it, it's going to go farther horizontally speaking. But the time in the air only depended on the height that it was fired at and the acceleration due to gravity. Okay, that's a long video for this. I'm going to stop here and then we'll make another video for the next part.